Why do we have antennas? I mean, when we think about what is going to be happening with our wireless networks, it's going to be important to understand exactly what role the antenna plays in that whole business. So, all right, I've got an access point and there's an antenna. Now what? Well, that antenna is receiving electrical current, and then it's converting that into an electromagnetic pulse, which generates a waveform, which then transmits from that center point, that center antenna, out. That's half the job. That's what we call transmit. Sometimes we'll flag that with a TX to say we're transmitting signal. We also, of course, are going to pick up incoming electromagnetic waves and convert them back into electricity where they can be processed and turned into intelligible signal. That's what we call receiving, or RX. So our antennas do that, and that's easy enough. But remember that the antenna itself is going to be designed in a certain way to do that job effectively based upon a certain scenario. Not all scenarios are the same. Sometimes you want an antenna that is going to be an equal opportunity player, just kind of a radius around the antenna allows everyone to jump on board. Other times, you're going to want to have an antenna that is directed, that almost shoots a beam of waveform in a specific cone from that specific access point, and that is, as a more directional standpoint, is going to be more effective for isolating that signal and sometimes giving it a greater degree of distance before it peters out. So describing the way that an antenna sends out that waveform is what's called the radiation pattern. And the radiation pattern is described by how it works horizontally and how it works vertically. And so we call that relatively the elevation chart, or E plane, and the azimuth chart, or H plane, for horizontal. So why they didn't make it H and V or E and A for elevation and azimuth, I don't know. I think they got confused somewhere along the way, but nobody asked me. The way that this is described, right, from a particular antenna is usually indicated with a top view of the horizontal plane, so you're looking down at it, and then a side view of the elevation plane. So you can say, okay, at the top of the antenna versus at the bottom of the antenna, how is that signal radiating out? Remember, there is no perfect isotropic antenna. We don't radiate evenly out in all directions. The support and the base of the antenna itself affects the way that that signal gets dispersed and affects the shape of that wave. Normally, when we look at this radiation pattern that we have, we're going to see it actually overlaid. So it'll be very common to actually see these two shapes, one on top of another. And that way we're able to say, okay, so here's what's going on horizontally. In this case, we have a nearly even distribution. Notice it's not perfect. That means that when we actually look at the radiation plane as it is measured in decibels around this particular access point, we're able to see the here in this H-plane diagram that, okay, it's not perfect. That's honesty, and that's what you're going to see when you actually look at the actual values associated with an antenna vendor. When we look at the E-plane, same thing. Again, from that center point, how does that signal radiate around vertically? That's the elevation plane. So we've got left and right lobes that are very common to see surrounding that. And so that means, notice, if you're right above or right below that antenna, are you going to get good signal? Look at it. Are you? No, it doesn't go out in an equalized bubble around the access point's antenna. See how there's all this dead space here, dead space down here compared to the horizontal plane? That tells you that you are actually seeing the way that this is being produced. Now, again, this is all measured in terms of decibels. So what we're seeing is the strength of signal in the various different degrees over the vertical and horizontal axis. This has nothing to do with distance. Distance and free path loss is a factor of what happens to that signal as it spreads out away from the launch point, from the emanation of that particular antenna, and is going to happen regardless of the antenna type that you have. It will have free path loss. If there's stuff in the way, it will have absorption that decreases the decibels of the signal. But at the center, as it's starting, what is that What does that signal look like? That's what we're able to see with these radiation patterns.